Morning. I'm Jeff Hammond, Executive Director at International Ground Source Heat Pump Association. Welcome to the June IGSHPA Town Hall. We have a great topic this morning. It should be very interesting. Before we get started and turn this over to Brian Urlaub, I do have a few updates for members. So we'll go through those here quickly and then we'll get started. So in the latest IGSHPA news, just a reminder, if you go to the IGSHPA website, IGSHPA.org, you'll find a training and events button. There are all the town halls, dig deeper webinars and training and so forth, but also the abstracts are there. If you'd like to speak at one of these webinars, this is the location where you would go. We are still accepting webinar advertising for 2025. So if you'd like to be involved, please go there. I have a save the date note. Our next annual conference is in the St. Louis area. It's at the Ameristar in St. Charles, Missouri, April 14th through the 16th, 2026. Make sure you have that on your calendars. More information will come shortly. In fact, here in the next month or so, you'll see the registration information, sponsorships, exhibitor information, and so forth. So that is here within the next few weeks. Our research conference is every other year, and this next one is in 2026 in Vienna, Austria, in cooperation with IEA. So that is in May 26th through the 29th, 2026 in Vienna. More information is on the website for the research conference. I'm thrilled to say that our 2025 edition of the C448 standard published on May 30th. This has been a long time coming, lots and lots of changes. It's almost 250 pages. So you'll want to make sure you get a copy of this. If you're an IGSHPA member, there's a pretty substantial discount. It's $175 for IGSHPA members versus $250 if you were to purchase that from CSA. So that's a big advantage to being a member. This has a lot of new information, including a section on district energy systems that includes the thermal energy networks that Brian's going to talk about here shortly. The IGSHPA Board of Directors decided to sunset the 2017 IGSHPA standards when this 2025 edition was published. So now this standard is the IGSHPA standard, and it's binational, US and Canada. So make sure you get a copy of this. It's really helpful for design, but also, if you're looking at language for local jurisdictions, this is very, very helpful as well. You'll want to get a copy of this, and don't forget the discount for members. We're building our databases. We could use your help here if you have applications that you've been involved in. This is a great way to make sure that we spread the word about the technology, but also it gives us a lot of examples of best practices. So if you have a project to submit, go to the IGSHPA website. It's under the About GSHPs. And this will be a good place to add your information. Also, our licensing and CEU requirements needs your expertise as well. If you'd like to get CEUs for this town hall, just include your name and your email in the chat. If you can't use chat, use the Q&A, and we'll keep track of that for you. We do have another method for obtaining those CEUs for your certification. If you're watching this as a recording, then you can send in the information to info@igshpa.org and just include this webinar code. If you're here live, you don't need this code. Just send in your name and email. But if you're watching this in a recording, that code validates that you've watched that remotely. And for housekeeping, after Brian is done, we'll be looking at the chat or Q&A. I'll be asking those questions for Brian to answer. This will be recorded. We'll have it on the IGSHPA website in the next few days, so you can watch this later on. A little bit more housekeeping. We have noticed that some people can't access chat. It might be a security setting. You may have a window that pops up like this. If you click OK to allow you to use chat, then you can ask questions. If you can't use chat, you can use the Q&A, and if you can't use Q&A, just raise your hand and I'll unmute your microphone. But in most cases, people can either use chat or Q&A, so that's worked pretty well. All right, I will now turn this over to Brian Urlaub. Brian, feel free to share your screen whenever you like. Brian Urlaub is the Director of Geothermal Operations for Salas O'Brien, where he oversees all geothermal projects. He's involved in all aspects of the projects from procurement to design, project management, and commissioning. He graduated in 1993 with an associate degree in HVAC technology and design from Chippewa Valley Technical College in Eau Claire, Wisconsin. Mr. Urlaub started out his career in the field, installing and servicing all types of HVAC systems. In 1996, he moved to inside sales and design and was introduced to his first IGSHPA course. He's been dedicated solely to the geothermal industry since 1999. He's been involved in multiple state and national geothermal organizations for the past 2 decades, such as IGSHPA, the Minnesota Geothermal Heat Pump Association, and Wisconsin Geothermal Association. He's currently on the IGSHPA Board of Directors and serves as Vice Chair. His current job as Director of Geothermal Operations includes such duties as collaborating with mechanical engineers on energy efficient designs, mechanical contractors on installations, drilling contractors on geothermal heat exchanger installations, and architects, developers on better understanding of geothermal technology and implementation of innovative geothermal systems. So it's my pleasure to turn this over to Brian. Thank you so much for joining us today, and it's all yours.
Excellent. Thanks, Jeff. I really appreciate the, sorry about that. Appreciate the introduction. I get a little, feel a little awkward always when people talking about me like that. Anyway, I've been doing this a while, but I really appreciate it. Yeah, today, and I appreciate you asking me to come in and talk today about thermal energy networks. And you know, we've been really fortunate as a company to be involved in this new kind of way of thinking about community thermal energy sharing, thermal energy networks, et cetera. You know, over probably 6 years ago now, we kind of got involved in our first one and been very fortunate since then to be involved in a bunch of them. And so I'm going to show you a little bit of what we've learned over the last couple of years, a few of the projects we've been involved with, and talk about a few things. But first, I'd like to just start out a little bit here quickly about the agenda. We're going to talk a little about the taxonomy of district energy versus thermal energy, because I see that there's becoming some blurred lines there. And so I'd like to just, you know, kind of start with that and really kind of go through that a little bit. And then talk a little bit also about site selection for thermal energy networks, because there's a lot of studies going on out there right now for these types of projects, mainly with either municipalities, cities, or utilities. And that's probably the most crucial and critical part of whether or not these become, you know, real projects, if they're, you know, financially viable, if they're constructible. And so really just kind of talking about that and understanding the site selections and what's really important there. And then we'll talk briefly about single pipe versus two pipe, because it's always an interesting conversation, you know, with other folks in the industry. Then we'll dive into some project examples and maybe a few things that we've learned along the way on some of those projects. So first things first, and I'd like to give a little shout out to Heat, because they've obviously been doing this now as well for quite some time. And Zainab and her crew have been phenomenal and kind of really driving this technology. And so I'm using their slide here to kind of talk a little bit about geothermal. And we do see this quite often. And I hear from people like, why do we use the term geothermal when it's really more geo exchange or ground source heat pump? The issue becomes really from an industry perspective. And when you think about the federal government and state governments and the language that's being used in writing policy and regulation. And so geothermal is the term that almost all of those bodies use for describing a geothermal heat pump system. So if we were to try to change that term this far into the game, I think would be very confusing and difficult, and could potentially put us in kind of a bad spot as an industry. So just real quickly, kind of what we want to show and highlight here is what we're talking about are the two on the right. This is what we call low grade or shallow geothermal. We're using the Earth's, you know, temperature to transfer energy and use that medium temperature to either heat or cool, and then use heat pump technologies to, you know, to intensify and distribute that energy. So not talking about deep geo for power production or direct use, really just the low grade energy. And then also, you know, just talking about district energy and thermal energy networks, you know, just to kind of clarify a little bit, because really when you're talking thermal energy, anything that moves thermal energy is under that umbrella, right? So you could, a steam system, for instance, in downtown metropolitan area with a steam plant, that's technically thermal energy distribution or district energy. Hot water, chilled water systems are district energy, but also thermal energy. So really with the difference in the taxonomy becomes how we're, and where we're intensifying the ambient temperature or the source energy and how we're delivering that to the buildings. Is it through a central system or is it a distributed system? And that's really the difference between what I would consider a district energy system and a thermal energy network. Now, granted, thermal energy networks kind of cover the whole gamut, but because a lot of, again, you're looking at the regulatory side of things, a lot of states' language are around thermal energy networks, because that's the original term that was kind of coined in this space. That's kind of what we're stuck with, although these are all really under that same umbrella. We're talking specifically about geothermal networks or thermal energy sharing between buildings in a two-way fashion. So you're actually able to take heat from one building, move it to another, and vice versa. So that's kind of what we're going to talk about today. Although I would say the 4G systems, which 4G and 5G is kind of coined by NREL and DOE of the different types of systems. 4G is more of your central plant. 5G is more of your ambient type systems with distributed heat pumps in the buildings. We're going to talk about 5G today. So let's dive into site analysis a little bit. Site selection and down selecting from a large site to a small site that is going to be the best site for a 5G thermal energy network is really critical. And there's a lot of things that kind of go into selecting that site. And it's interesting when you look at all the projects that are kind of happening today around the country. Most of them are happening in older areas with an aging building stock, very aged HVAC systems, which make it very difficult to retrofit and convert to geothermal. As most of us know in this industry, especially when you're looking at a hot water system, the high temperature hot water is very difficult to retrofit to geothermal. So to a geothermal heat pump system. So when we look at sites, yes, we want to demonstrate especially in the pilots that, we can do the difficult jobs, but maybe we should start looking at, let's start out with the easy jobs first, knowing we can do the difficult jobs, because what happens is we end up with cost structures that end up being a little bit out of touch with reality to some degree. And then the industry looks at it and goes, okay, maybe this isn't the right infrastructure technology to transition, to the future with electrification and decarbonization. So age of the buildings, the type of systems in those buildings is really critical. What we would really look at when we're looking at these sites is let's look at, areas that are maybe electric or gas constrained, rather than putting in a new gas line and expanding that and paying for the next 50 years, because once you put that gas line in, it's staying there. Looking at those areas that don't have gas or a constrained electric site, maybe that's a better opportunity for the thermal energy network, because we don't use as much electricity. We don't have the peaks, which I'll show you later, which can help the grid. And we don't need the gas lines, and we don't have to worry about that one or two customers that the utility still has an obligation to serve down the road if everybody switches away from gas. So I think those are really critical components to selecting these sites. Also, obviously, having some type of a thermal resource available that's close. Density is very, important, because for every, 100 yards of pipe, having multiple customers connected versus one customer just, helps the cost benefit. So your customer base, the number of customers, the density, the load diversity is also really important. So all these things kind of go into a rubric, and you put weight to those kind of metrics, and then you try to develop some type of a scoring system that's going to really help you, data-driven, analysis to help you select the correct site that isn't just from either, people wanting to do it for another reason, that isn't data driven, because really you have to look at the data to select these sites to make sure that they're going to be constructible, cost effective, have the best benefit for the cost, for the community, et cetera. And So those are all the things that we kind of lump into these rubrics and scoring metrics. And, it can be very, very challenging, again, depending on how big of an area you're looking at. There's a lot of projects right now, they're looking at total states of where's the best sites. Well, that can be very challenging. You've got to get through some very quick yes and no's to just eliminate a lot of areas and try to, funnel that down quickly, or you could be there for years trying to analyze where to put these systems. So it can be a challenge, but these are all things that, that should be considered. And then back to the thermal assets, we've primarily looking at geothermal systems. You've got to find some open space, whether that's parking lots, hardscaped or green cut, greenscape. We've got to find areas for geothermal boreholes, because that's primarily the main technology right now in this space that's driving the thermal energy for these systems. Okay. Now, if you have wastewater, if you have waste heat from, some type of a commercial building, data center, grocery store, what have you, that all really plays a good part. But we've got to have something to really start with, and that's generally geothermal. And so, analyzing the sites, figuring out what's the load, number one, of the building stock that you're looking at, then looking at the available area, figuring out, okay, how much of that load can we cover with the area that's available. And so this is just kind of showing you like, okay, what, if we're going to hybridize this and try to really take full advantage of the costs, what does that look like? And so what's the unbalanced heating and cooling? And, when you're doing high level site selection studies, you're not getting into full detailed energy modeling of all this. So you've got to get to these answers fairly quickly. You've got to have relatively good sources for data to determine energy loads of buildings, which, you can use a lot of different sources for that. Then you've also got to get some really good tools developed, which we've obviously been doing geothermal a long time. So we've got a lot of tools developed that we can get to these answers very quickly without spending a lot of time, and really determine like what's the best site and how much capacity do we have for that site, and does that make sense? And then you can start toggling on and off different buildings to really figure out what's the best mix for that site, for the energy that's available. So there's a whole lot that goes into this site selection, and it gets to be very, detailed. But it's critical, because when you pick the wrong site, the project either doesn't go forward, or the costs come in so high that, the cost per customer for the client doesn't make a lot of sense. And so it's hard to justify. And if you're taking this to a utility into the Public Service Commission, they're going to question that. So you really have to understand that, how and what all goes into that. The single pipe versus two pipe, conversation, I just want to touch on briefly. I'm a big fan of the single pipe, obviously. We've done a number of these types of designs and implementations. And, for me personally, I think if you do it right, it offers you the greatest flexibility for locating your thermal assets. It gives you the best flexibility for expansion. It gives you the lower cost in pumping energy. It gives you lower costs in pump sizes and pipe sizes and installation costs, because really, if it's done right and you have the right distributed thermal assets throughout that system, you're only concerned about the temperature profiles between each energy source, not all the way around. Whereas the two pipe system, you generally have, one energy source, and you're delivering that same temperature to all the buildings, which for the buildings is great. They all get the same temperature, same efficiency. But if the single pipe is done right, honestly, the efficiency, and I'm going to show you this here in a minute, it isn't much different. And they'll never know the difference from an online bill at 10 or 12 or 20 cents a kilowatt, because the efficiencies are so close. And so to have the extra pumping energy and all the additional piping costs, and, just putting pipes in the street, one pipe versus two pipe, all that coordination and space, it's a lot. So for me, the thermal energy network space really the single pipe is the driver there to start with. And if it doesn't make sense, okay, you can move to a two pipe. But I think at least from our perspective, we always start there as the first kind of design approach. And then we'll analyze the site and make sure that it is the right approach. But most often it is. And it's a little different design. You really have to understand how those systems work, how you pump them, how you model it. And so you really need to understand that, because it is quite different than a two pipe. And, my last bullet there is that we try to maintain a 5-degree delta between any energy source, so all customers get fairly close efficiencies. I'm going to show you a project here where we actually broke that rule. All right. So let's get into some projects. And again, single pipe ambient loops, primarily what I'm going to talk about here, because that's generally what we do when we talk thermal energy networks. And again, the great thing about this is that energy flows in both directions. Whereas if you were doing like a hot water, chilled water, generally your energy is going to one direction. And then depending on your central plant, if you've got simultaneous equipment that can take advantage of that, now you can do that. But if you're using a boiler and a chiller, you're not really able to do a lot of simultaneous. So unless you're using heat pumps and can take advantage of that, this is a great way to share energy, especially when you're doing heating and cooling, at the same time. And just real quick, just a little bit more background on Salas, but this is some of our experience. I mean, we've got a number of these projects where we've either done studies, done designs, or fully implemented. You can see there's 6 or 4 projects on here that are actually in operation, a number of projects in design. So we've got, I think for this particular space, a lot of experience. And I'm just going to kind of go through a couple projects. And if any of you have ever heard me talk before, I've talked a lot about this project because it is the oldest one out there. It was the first one that was actually implemented in North America. That's a true single pipe system. That's what I would consider a utility grade, meaning everything is located in the street. So as a utility would operate a gas system or a water system, everything is located in the right of way. Nothing is on private property. And so you can see here, there's about 2 miles of 6-inch pipe. There's 11 pods of 144 boreholes scattered around the site in very strategic locations based on the energy profile of the homes and how they interact with the single pipe. And then we have 4 pump stations that actually circulate the main system, the ambient loop. The reason why we went with 4 here was primarily for phasing and resiliency. It ended up being that that was a little more challenging to control and to pump. So the little lesson learned there. But it did offer, and they didn't phase this project. They ended up building it all at once, which was, not the original design intent. It was going to be phased from left to right. So, but now those bypass lines that you can kind of see at each of those kind of quadrants offer us, some resiliency because each system could be pumped independently. If, let's say, a pipe was hit in the street, you could isolate that section and still pump the other sides. And get some resiliency out of that. So, but 312 homes, all the there's no backup energy here at the ambient loop or infrastructure location. It's 100% geothermal. Each home has a electric strip heater in the heat pump, which is very common in residential applications. But that would be the backup if the system went down. That's your backup heating source. Is electric. So there's nothing in the infrastructure itself. There's no pump house here. These are all below grade vaults where all the pumps are located underground. And again, no more than 5 degrees between each energy source here on this system. This was our first, this was about 6 years ago. This was our first real use of what's called Transys. It's a software program that runs a dynamic transient model of the system and really can model any point in any parameter within the system. And so we used that to model the system because this was new to us at the time, when we designed this project many years ago. And this is kind of the schematic of how that gets laid out. And then these are just some of the graphs kind of showing you what Transys offers, in a modeling perspective, because what we need to understand again is what is the temperature profile of that ambient loop and how does each customer get affected by the different temperatures around that loop. And this is showing you that really no one customer is experiencing more than a 5-degree difference from any other customer, which again, back to the efficiencies and on bill, utility costs, that's negligible, especially for residential. Okay. And then we can also see here, just a full temperature profile. This was at year 10, is, the coldest and warmest part of the year shown here on this graph. So you can see that the system modeled was going to perform very well. And what we're actually finding in real life is that it's performing extremely well, better than expected in heating, and a little bit worse than expected in cooling. What we're finding out is that the Energy Star homes that were built here were very tight and very energy efficient. So they actually have a little more cooling load than we anticipated. So again, we ran a lot of sensitivity with Transys around this project. So we still have enough capacity and we're not getting over the 90-degree threshold, but we are definitely over 80. And again, anytime we run these scenarios, we run it, 10-year, 20-year scenarios to look at the health of the system and how it's going to perform over the long haul. We also look at the sine wave of the loop temperatures and how it's performing, between the minimum and maximum, and really look at your troughs and your peaks to figure out, where do we need to move things around? How do we balance the system out so it performs across the entire network? And then, of course, the beautiful thing about, in my opinion, as well, these single pipes with distributed thermal assets is that you don't get the thermal creep in some of the bore fields you would have as, let's say, a campus where you've got one large bore field with 600 bores, and you've got all those in a grid pattern. And you're going to definitely have a little bit more impact to the center of that grid by putting heat in or taking heat out. Whereas when you have these, if I go back a second here, all these boreholes are in a straight line, and none of them are in a grid pattern. So you have a lot of undisturbed soil all the way around these bores that they're not going to be impacted over the long term. And that's what we've shown in the model. And that's what so far, what we're seeing now. Of course, we're only in year 2.5. This is our second summer of operation. So, but that's what we're anticipating, what we would expect in watching the trend data. All right. Now, the other thing I just want to touch on real quick about single pipes, because I hear a lot about pump energy. And, if you're going to compare this to a single building like a school, and if you look at the ASHRAE handbook and you look at, what Dr. Kavanaugh would consider low pump energy for a geothermal system, these systems would not qualify as an A or a B grade within that ASHRAE standard. But these are much different systems. Of course, you're going to have more pump energy here because you have a network that you're trying to serve, a whole bunch of buildings at once versus just one building and one loop field. So you've got, ground loop pumps, you've got ambient loop pumps, you've got building connection pumps, and then you've got pumps within the building. Now, of course, your building by building pump energy is less than if they had their own geo, because they're just connected with 2 pipes to the ambient loop, very low pump energy. But the infrastructure pump energy is something to be, considering. And you always want to look at this. And that's, again, back to the single pipe. If it's done right, and you model that correctly, and you look at your delta T's from energy source to energy source, and you put in more than one energy source, so you can bring that total flow rate down, it does make a big difference. And you can see here, this isn't awful for, 600 tons or 500 and some tons of capacity, 650 tons of capacity. We're not that much worse than a typical building if it was of the same size. So again, just want to make a note that pump energy is critical, because this is all parasitic loss. There's no benefit to this. And so you definitely need to keep this in mind when doing your design. And then, of course, in your operation, when you turn a system on and you're going through your optimization, cutting back on your pump operation is critical. Anytime you can reduce pump speed, you want to do that. Just take that energy and take it down. So there's no reason to over pump these systems if it's not needed. And we're already seeing that on some of these early systems that have been installed, where they're not pumping them correctly. They're pumping them way too much, and they could definitely, save some energy. All right. And these are just some pictures of the installation of this particular project. Again, a few lessons learned here. Number one, below grade vaults with pumps and so forth down in a high humid salt environment. You definitely have to treat or coat or insulate, make sure everything is completely sealed to prevent corrosion, because you will have corrosion. So that's definitely, a key thing if you're going to do below grade vaults with more than just pipes in those vaults, like not a typical vault from a ground loop heat exchanger, but actual pumps and other components. Making sure you understand how to get the air out of the system and all the dirt and everything that goes in. That this particular project did not go well from a flushing perspective. They tried to use a hydrant. A hydrant couldn't push, 2 miles of 6-inch pipe. So there was a lot of air in the system. There was a lot of stuff still in the systems. They ended up having impacted impellers on the pumps right away. So they had to, pull the pumps and clean them and change impellers. So, just making sure the systems get flushed and purged is so critical, in understanding how to do that. Because these are large systems, large volume. They take big pumps in order to get the air out and get the debris out. All right. In these ambient loop systems, if you're going to do multiple in-series pumping, what we learned here is that the first connection or takeoff out of the pump vault is going to see the highest pressure, obviously. Well, some of those residential homes, because there's no energy transfer station, they were seeing 150 psi at the heat pump, which is borderline, what we want to see with the piping and the hose kits, et cetera, and the materials that were used on that project. So you really have to pay attention to your pressures. Now, a lot of these other systems that I'm seeing out there, there's only one pump that's being used to pump the ambient loop. So, you only have to worry about that first building, second building off of that pump station. And then from there, the pressure goes down. So, but it is something to consider, especially if you don't have a heat exchanger to isolate that. And then again, just optimizing your pump operation is really critical. The other thing, another project, we're in the midst of a design here. So this has not been implemented, but I just wanted to talk about a few things that we've learned here, which I think we've also learned on a few other projects, especially related to costs. But this is the Haverstraw project. We've got the red loops, which are the two first pilot loops that they're just in design of, and the purple loops are the hopeful expansion of the system down the road, but not part of the actual pilot project. So the west loop, which is shown here, we've settled on 2 bore fields and a large sewage heat recovery system. They've got a 16-inch pressurized main that runs right through the site. So we've got a pump house that's shown there on the north end of that bore field. So the manifold for that bore field will be in the pump house. The sewage heat recovery equipment will be in the pump house, and the ambient loop pumps will all be in that pump house. And then there'll be a vault below grade for the other bore field with a pump in it down on the south end of the loop. This is a pretty large system. This is all commercial buildings for the most part, a school, a community center, city hall, or village hall. You've got a big office building. There's a bunch of other buildings, some multifamily. So it's a very large system. So we've got 72 bores, and we've got 2 of the Shark 880s, I believe, designed right now on this system. So a lot of energy required to maintain this. And I think this is a 10-inch main for an ambient loop that runs around this particular site. And one of the things to keep in note or to think about when you're looking at these single pipe ambient systems, if one building is driving your flow rate, take that building off and do a parallel system with that building, because like this particular instance, the school was driving the entire ambient loop flow. So if we can just parallel that off and we have the bore field and the sewage heat recovery in that kind of location, we can serve that school differently than just keeping it as a typical connection point like every other building off of that loop, because the large load really drives the total flow of the ambient system. You can't have less flow on the ambient than you do on one particular takeoff. So what we've done on a couple of projects is we've just taken that particular building and put it in parallel, and then feed it from that energy source to really help reduce the cost and size of the rest of the system. And I think that's really critical to trying to maintain, because we want schools, we want large buildings on these systems. But if you have one large building and a bunch of small buildings, that large building is going to be the driver. It's also going to drive your costs of the whole system. So you got to figure out a little different way to do that. Okay. And then we're just kind of showing our different thermal asset dispatch model, and how they all contribute to the system here. So this is the pump house. And, one thing I'll just note about pump house is, these are going to be the biggest cost in the system. And so, minimizing floor space, minimizing, what I call dance floors in the pump room. You don't want a whole bunch of open space. Make these as small as possible, still be able to service everything. It's really critical, because these are going to be very large costs to the overall project for just housing equipment. And so it's, and we also don't need to make, if we really don't want to make them and pay for showcases, this building is really just going to look like a lot of the other buildings in the neighborhood. Very, inconspicuous. It's going to just be a brick, facade, and, pretty standard building to try to keep the cost down. And again, this is going to be unmanned, pretty much a dark room. All this is just housing equipment that's going to operate, and based, from a control system. There's nobody that's going to be actually at this facility, full time or even 8 hours a day. And then we've got the East Loop, which is a little bit different because we've got a large new construction development on the East Loop, which is down on the peninsula there. There's going to be four new larger 6-story multifamily buildings. And so that's, a little bit of a challenge, I think, with new construction because of the timelines. You have to work out the timelines that, this is all going to go in with their schedule. And, how does that work? What could we do to maybe do early bid packages, or maybe how we could phase the project a little differently to make sure that you meet those timelines? Otherwise, that's a non-starter from the beginning. So, collaboration with the developer is critical, really understanding that. And then again, how do we put in some infrastructure to work together to, again, share costs and minimize costs. And that's really critical. So this area down by the water is going to also be a park. And so what we thought was, why not put the pump house down there and then add public bathrooms to that pump house to have a dual purpose. So you don't just have a cost of infrastructure, but now we have another purpose for that building, which can help share the costs and be a public benefit. And so we've actually designed that within the system. We've got a number of bore fields. We're also using sewage heat recovery out of all the new construction multifamily buildings, and also a river source to help provide enough energy for this entire site, because it's very energy intensive, and we did not have enough room for geothermal boreholes at 800 feet to handle this entire site. We would have had to make it much smaller. And again, this is just kind of showing you, kind of how we dispatch some of the thermal assets and the piping of the system, and what that looks like. And again, we did a full river heat exchange study here, and then have gone into some design of, because this is not a closed loop river system. This would be an intake and an outflow. And so, getting this permit and everything else is going to be a challenge, but we're up for the challenge, and it should be a pretty interesting ride getting through all this. But this is a really important part of the system and learning, I think, number one, but number two, a tremendous asset to be able to utilize if possible. So reduction of 20 to 25 boreholes with 800 gallons a minute from the river, which isn't a large system, but at $50,000 or $60,000 a borehole, that's a few $1,000,000 reduction there. Obviously, then there's cost to all that. So it might be a wash, but great learning opportunity here. And then again, back to the pump house, you can see we've got our pump house with all of our equipment, but then we've also got the bathrooms included here. So just trying to do kind of a dual benefit to the community, as well as, not making it stand out, kind of blending it in, but, having somewhere to put all of our infrastructure. And again, some lessons learned here, just trying to make sure that we, minimize the cost of the pump houses is really important. Understanding, the constructability. We've looked at, backup boilers and some other things. We've done a lot of sensitivity around that. At this point, that's not included. We're just using 100% geothermal or sewer or river to heat and cool this entire project, as well as domestic hot water for the majority of the commercial buildings, not the new construction, but the other buildings. And and then just we're going to learn a ton about all the regulatory and permitting issues related to tapping a pressurized sewer main and also utilizing the river. So I think that's going to be, we've already gone through a number of meetings with a lot of different regulatory agencies, and that'll continue. So that's going to be the biggest, I think, lesson learned here on how to do that. Another project to talk about, I think everybody's probably familiar with this project. It's the first one in the US that's been implemented with Eversource Energy in Framingham, Massachusetts. You can see the first phase there, the loop on the right, has been installed and in operation and also performing better than expected, which is great. We were involved as a sub-consultant and did the Transys modeling, for the first phase, and it's working really well. And it's, again, very interesting looking at the data and understanding how these systems have such a large mass in the inertia, and the amount of energy it takes to move the temperature needle on these systems is tremendous. And so they get through peaks very easily because you're already at such a low, moderate temperature that to move that temperature a couple degrees one way or the other takes a long time and a lot of energy. And so, that's been an interesting kind of learning, on this particular site. But we were involved also with heat and Eversource on phase 2, which is expanding this thermal energy network, which would be the first expansion project in the country. And we learned a lot. And I'll kind of show you a little bit about that, but it was really about how do you connect the two, hydraulically and thermally and not impact the first loop. And then also, if you notice, there's a bore field at the top of the project site there near the school. That's where the other new bore field would go. So now most of your energy is all right in that location. And again, we have a driver building, we have the school. And so, thinking about that and understanding that school and how it impacts the total ambient loop, we wanted to isolate that hydraulically, serve the school directly from that bore field in parallel. Then we can reduce the entire second phase of this project and the ambient loop size and the flow rate and the pumping. And then we can hydraulically connect it to the first one. And we're not, we don't have dramatically different flow rates that we're dealing with, number one. And then number two, how do we then connect those two and not impact the first phase pumping that's already installed? We didn't want to have to go back in and upsize those. And so initially there were just some T's put in at the north and south end of that street to expand. But the pipe size was the same all the way around, 8-inch pipe. Well, once we started doing our hydraulic analysis, and I'll get to that here in a minute, we realized real quickly, that's not going to work without changing those pumps. So how can we make this work without changing the pumps? And I'll show you here in just a second how we accomplish that. But here's the two kind of loops if they were left alone, and we did these two independent phases and didn't mix them thermally with the amount of bores we could get on the second phase because we were very limited on space. You can see that, they weren't going to operate quite the same. So we would benefit from thermal sharing here. And this is kind of showing you, throughout a couple of years, what it looks like and how different they actually would operate. Now, it's not, massive, but they would operate differently. So we can benefit from sharing energy with one another. So what we came up with is a 20-foot section of pipe being replaced rather than the entire length of that north and south street. And if we do it in both locations, the top and bottom, we don't impact the hydraulics and the pumping because we can upsize that to a 10-inch pipe. We can flow both flow rates through that 10-inch section without increasing the head pressure on the first phase pumps. And now we can still get enough thermal sharing in those two 20-foot sections of pipe to actually make a difference. So that's what we came up with running through Transys and in our hydraulic pipe flow models to really do this cost effectively. Now, the downside to that is we don't have valves and T's already in place to make this work because we didn't go through this exercise on phase one. We're doing this now on phase two, so it will be a challenge. They will actually have to, shut the system down, cut the pipe, put the valves in, get the pipes replaced, and turn it back on, and hopefully do that very quickly and do that in a time of year when they don't really need a lot of energy. But all the customers will have to be down for, a day or two or three, depending on how long it takes. So that's the downside. But great learning opportunity here to how do you expand these systems and think about that. Think about how you do that, as if you're going to keep doing this and share thermally and hydraulically. Okay. So again, if we show how these two mix together now, so you notice that other graph, we had kind of a difference of a few degrees between the two loops. Now you can see at each point where they mixed 3 and 1, right here and right here, we actually flatline the two together, which means they 100% mix to the same temperature. And then once they go back out into their respective loops, they go back and start, obviously changing temperature based on the energy profiles of those loops. But those two 20-foot sections bring the both temperatures to the same temperature. So we only needed 20 foot of a 10-inch pipe to make that happen. And so that was really interesting, learning experience throughout this project. Now, of course, we haven't implemented this yet. We're hoping for the DOE funding soon and Eversource to move forward with construction. So that'll be, really neat to see how that all works out. Again, so now you look at the graph and you can see that they're basically the same temperature throughout the year across the board for both systems, which is the goal of, thermal sharing. And then, of course, the benefit of that as well is that everybody gets a little bit better COP. And so we modeled the COP of these systems, and just to kind of highlight that, talking about thermal energy networks as a whole, because of the mass of these systems and how they're designed, if you were to do a single family home or a commercial building and you design it around a certain parameter, you generally hit that parameter, like 32 degrees, for instance. Um, you're not seeing that in these thermal energy networks because, again, of the flywheel and the mass of the fluid and the volume that it takes to change temperatures and of course, the mass of the Earth that we're connected to. And so you look at the COPs of this system. You're driving from 4 to 6 and 4 to 5.5 COP in heating, and those are throughout the entire year. That would be, the high point for a standalone system, not the average. And so we're seeing tremendous efficiencies and really good, COPs across the year, not just, the seasonal averages, but even at the worst times of the year, which I think is a really good testament of why these systems, can work and can be very effective in providing efficient, low carbon solutions to, to the infrastructure that we need to move to. So again, I've already talked about this, but these are the lessons learned. Again, how do we mix these systems? How do we look at the hydraulics of these? Where do we place the thermal energy assets in these single pipes? Now, again, you're limited based on the site. So if you can't get a good distributed system, then maybe a two pipe would be a more effective way to do it. Again, so you have to look at the site and really that's kind of the determining factor of what direction that you go with these systems. Another real quick project to touch on here. I know I'm getting close to my time. This is an interesting one just primarily because, well, we did a lot of early analysis on a lot of different things here, but this was going to be a closed loop project. And then we got into the design, realizing that there's a massive aquifer 300 feet or less underneath this site. We moved quickly to an open loop system. We could pump thousands of gallons a minute here with no impact. So we don't need that, but we could. And so what that does for us is it really drives down the ambient loop flow rate because we have an open loop with a stable supply temperature that now we can go from that 5-degree delta that I talked about to 12 or 10 or 12-degree delta, and everybody's still extremely efficient, yet we can reduce our pump horsepower, pump size dramatically. And then this just kind of talks a little bit about, again, that diversity in load. We have a big commercial building and 3 multifamily buildings and how they actually can share energy. And this is in the Northwest. So you've got a very balanced kind of weather profile. Number one, you have really good heating load, but you also have very good cooling load. So we're finding that the Northwest is actually, from a diversity and load profile perspective, fantastic location for this technology. But again, back to the flow rates. So this would be on the left would be your flow rate for a 5-degree delta between the 4 buildings. Okay, well, that's fine. But with an open loop system, we don't need to do that because we're still just providing fantastic, medium temperature to the buildings that are extremely efficient. So we went to a 12-degree delta just to model it and see what it looks like. Look at our difference in pump energy and our flow rate. We went from 2,200 gallons a minute on our peak to under 1,000. So we cut everything in half. Pumps, pipe size, everything goes by in half, which was really a huge benefit to the cost of this project and also just the operational cost long term, for the client and the owner of this system who has to pay for that pump energy. So then, this is just kind of showing the temperatures of the buildings and how they move around the site. This is your temperature profile of your ambient loop. And again, 5-degree versus 12-degree. Well, sure, our 12-degree has a little bit more peaks and valleys, but we're still between, 59 degrees and 71 degrees because of the open loop. We don't need to do any better than that. This is an extremely efficient system. So, that's why you have to look at these different energy sources and really figure out what's the best option for these sites so we can drive down the costs, drive down the parasitic pumping energy, and really pay attention to that. And thankfully, we've got an amazing aquifer here that we can do an open loop system because that makes a huge difference for the viability of this site. And also the cost of the open loop wells versus closed loop. Number one, we didn't have enough space on that site to do closed loop for 100% geo. Couldn't do it. So that also was a huge benefit because now we went from a hybrid system to a full geo system and lower cost. And again, here's your annual COPs between the two. Look at your 5-degree versus 12-degree. I mean, you're still at a 5 COP. Why do we need to do better than that? We don't, right? That's an extremely efficient system. We're going to be much better than any air source product on the market in this, even in the Northwest where you don't have extreme temperatures, or at least heating temperatures, which I'm going to show you here in just a second, how that impacts the grid. Okay. Because that's also really important. So again, here's just your kind of monthly average COPs. Again, 12 degrees and this is building by building. So it doesn't matter which building you're on, you're still getting really good efficiency across the board, even at 12-degree delta. All right. So again, conclusion there, we can reduce pump energy by making sure we're looking at that holistically. And then looking at energy, because this is a gas company that's looking at this project, but working with the electric utility is extremely important. We talked about electric constraints. As we electrify buildings, what's that going to do to the grid? Well, when you want to look at geothermal in a system like this with these efficiencies versus an air source heat pump, which is the baseline, because they're going all electric, what does that look like? Well, here's your difference, your total summer peak and winter peak of the system. And then let's compare that to our baseline. Okay. You're at 633 and 875 with your air source heat pumps in a total of 2,500, megawatt hours. So a huge difference in energy. And then this is the real big one. Look at your 24-hour peaks, both in winter and summer. And as we electrify buildings in the northern climates, we're going to be going back to winter peaks. All the electric utilities are very concerned about switching to electric or to winter peaks. So how does this impact us? If you look at, the baseline versus geo and the efficiencies of this system, we're doing tremendous good for the grid during these 24-hour peak periods. And so this was extremely important to show to the electric utility and the developer that we're doing, we're electrifying the right way. We're not negatively impacting the grid just to say that we're decarbonizing. Okay. So this was really important work that I think was shown, to that electric provider. And again, so we just did all this analysis both in, across the board from including pump energy. You look at that top left graph there, we include all the pump energy as well, which is, not insignificant, but overall not nearly as much as obviously the heat pumps, but does still play a role. So we've got to model everything. We've got to do this on an hourly basis. We've got to be able to show these things, accurately to all the stakeholders, because this is really important stuff that the Public Service Commissions and everybody wants to see to make sure that we're doing it right and we're not negatively impacting, one source or the other, or one provider versus the other. Okay. So again, lessons learned, kind of talked about that, but just looking at different thermal assets, like, sewage heat recovery is another big one. We looked at it here, but once we went to open loop, there was real no need for that. Okay, because open loop is such a stable, low cost thermal asset. And the last one I'll talk about real quick here, I got 5 minutes. This is an interesting project because I wouldn't necessarily consider this a utility grade, even though it's going to be a utility project, but there's nothing in the streets. Everything was decided to run through the buildings and through the courtyards to make this happen, and then put all the bore fields in the courtyards. But a couple of interesting things I just want to point out. Again, space is a big concern. This is going to have to be an angle drilled or incline drilled bore field system because there's no space. There's a ton of utilities that run through here. Thankfully, they have, pretty open basements. We can run in and out of the building's basements to run the ambient loop. We do have to cross a street to get over to the building on the right over here. The ambient loop pumps are going to be in the old steam boiler room. And so, looking at the system, we have 7 buildings, and we're kind of limited a little bit on where we can connect our bore fields, and then, which direction should we flow the water to make sure that we're somewhat balanced. And then also, do we want to have a hybrid system here? Initially, I think we started out at 80 boreholes, and then we were going to put some boilers in, and we dropped it to like 70, I think, boreholes or so, somewhere 70, 72. Well, then working with the building team, and they had goals of reaching 20 BTUs per square foot on a peak heating basis. So they're doing envelope improvements to reduce the peak to 20 BTUs max. When we go through all those measures to do that, and we modeled all that at the end, we ended up realizing we don't need boilers. But let me just show you a little bit of when we were looking at the boilers and how that kind of impacts whether we want one boiler in one location or two boilers, one at each location. How do we want to do that, and how that kind of impacts things. Okay, so just kind of show you that a little bit. That's just the load profile there. Obviously, again, we have 7 buildings. We have 2 bore fields. So we're showing how those bore fields, and again, trying to maintain that 5, 6, 7 degrees. We were going through that analysis of, what's the right delta T here? So we had, a delta T of 2, a delta T of 4, a delta T of 6, and really trying to figure out what's the optimization there to minimize pipe size, pumps, costs, and then pump energy. And again, just going through that iteration because that's critical to, making these projects viable. And again, just looking at your thermal assets and how they stack up, because we had to put a certain amount of bores in each location, and trying to make sure that we're optimizing that. But it was very difficult because it's a challenging site with all the utilities and space constraints there. So then we looked at, okay, let's add a boiler, let's reduce the bore field, and we put the boiler in the old steam plant, and then just use that boiler to try to get enough energy in all the way around that loop. And what happens to the system? Yeah, it works. You can do that. The boiler will, if you manage it right, the boiler will provide enough energy and make it all the way around, okay, and hit the last building. But it does take a little bit more energy, okay, because number one, you have to make sure the boiler energy isn't going into the ground. So you have to maintain, your ambient loop less than your bore field supply temperatures, or energy goes the wrong way. So you have to model all that, kind of try to optimize that. So this is kind of what it looked like, but we weren't using a lot of boiler energy overall as far as BTUs, but we were hitting a pretty good peak, which again, thinking about grid constraints, just electric service constraints at the site, so then we looked at 2 boilers, 2 smaller boilers. Okay, we'll put one at each location of the bore field. Let's look and see what happens there. And so then we looked at that scenario again, and then now we're looking at the 2 boiler scenario. You can see here the second boiler wasn't hardly running at all, so we had to continue to play with that, optimize that, and size those correctly and set up your operational, dispatch models correctly. You're using it a little, but not a lot. And so that way you're not impacting your peaks dramatically. You don't have to have massive boilers and so forth. So this is kind of showing you, if you were looking at just the peak electric, that's that little bar in each graph. So this is just with geo, no boilers. This is if you had one big boiler and that's your peak. Okay. This is the peak KW 350 with one boiler. Then if we had 2 boilers, 2 smaller boilers, we're down to, 275, which is better. But again, to electrify these buildings and thinking about grid, you kind of have a little bit of a trade-off there that's not terribly beneficial. So we really wanted to get back to the full geo only scenario. And in order to do that, what did we have to do? We had to tighten up the buildings. And so that's a really big lesson learned here, is that building envelopes, building loads are, make a huge difference in these projects. So back to my earlier comment about site selection and thinking about the aged building stock and the building envelopes, you end up with issues like this. Whereas if we started to think about the low-hanging fruit, new developments, new construction, or even newer developments that maybe are on a delivered fuel that need to be retrofitted, to get them off a delivered fuel rather than extending gas lines, going in with a thermal energy network, So those are kind of the things that, in my mind, we need to all be thinking about when looking at these projects. Because going in with a bunch of electric boilers, sure, you're electrified. Yeah, you're carbon free on site, but what are you doing to the grid? How does that impact the grid? If we do this all over the place, we're going to have bigger problems. So, we can't just throw electric boilers at everything. Maybe some storage here could have helped, something like that, but we didn't get, we didn't analyze that. We didn't really have any room for storage necessarily. So again, I kind of went through the lessons learned here, but the great news is no boiler. We're down to 62 bores and no boiler with the buildings being tightened up, which is a huge, in my opinion, a really big deal. So look at that, right on time.
Right on
Thank
time,
you.
Brian.
Appreciate it.
Thank you so much for a great presentation. Fascinating information here. We do have a few questions. It's right at 11:31 a.m. Central Time. Do you have time to stick around for the questions,
Yep,
or should
sure
we
do.
come back? Okay.
No problem. Yep.
All right, so Natalia has a question. Can houses in the same loop have different temperature settings? If so, is there a min-max temperature difference that the person can select for their homes? Is this different for dual pipe systems?
Yeah, that's a great question. No, I mean, there is really no constraints on each individual building owner, homeowner, where they can set their comfort level, and we always do a lot of sensitivity around that, when we design these systems to understand, what if a bunch of customers wanted to keep their house at 74 versus 70 or, whatever the case is, and just see what that does to the load and how that impacts things. Now, on these larger systems, especially for residential, like at the Bercy Glen project, that didn't have a lot of impact. There was more impact about if we didn't model it correctly and got the loads off by 20%. That's a much bigger deal than just adjusting a thermostat. What they have to be more careful of is, the setbacks just with any geosystem, especially residential, is, your auxiliary heat coming on in the winter. But no, in a two pipe versus a single pipe, again, doesn't matter. It's, we're providing a certain energy source to that heat pump, whatever that delivery temperature is. That heat pump, as long as it can operate within that temperature profile and then is sized correctly to deliver the BTUs at that temperature, whether it's the peaks, heating and cooling, then they should be able to keep their comfort level at whatever they'd like.
Thank you. All right, Ruben has, I think this is more of a comment than a question. Good point about controlling costs in the pump house / energy plant. Often the owner wants to turn it into an architectural multi-use showcase, and then those high premium costs burden the energy system financials. It's important to separate these costs in analysis and marketing. Any comments on that? I think you sort of said that already.
Yeah, I mean, we've seen that on a couple of other projects, and there's no getting around having these pump houses. I mean, I do like the below grade vault idea, but it's certainly a much more challenging position from an owner and operator and maintenance perspective, and replacing equipment, down the road. Also, just wear and tear of being in a high humid environment. Obviously a pump house is much easier to access and go in and check out. But again, how many of these communities are going to want to see pump houses all over the place? So we've really got to get creative and think about how we kind of blend the idea of having above grade infrastructure versus below grade. The cost of that infrastructure, below grade obviously is lower cost because you don't have to have all the architectural features and roofs, but not necessarily always, because depending on the size, then of course, if there's groundwater, having access in designing those correctly and the size of them and where do you put them. So that's a really interesting conversation. I think every site's different, but as a whole, the industry really needs to think about those things because it's critical moving forward that those are done thoughtfully. And, otherwise you're going to start to see these super high costs, and then everybody goes, well, geez, this is never going to pan out, because of the cost. So good point.
Very good. All right. So we have time for one more question from Austin. He asks, are you running into any regulatory roadblocks trying to implement an open loop network requiring thousands of GPM?
Not so far. I mean, we've done a number of open loops, around the country. It depends on the jurisdiction. It depends on location. It depends on the aquifer. If they're non-drinking aquifers, we generally don't have too much pushback. If it's, like in Minnesota, for instance, where I'm sitting, as soon as you penetrate any of the drinking aquifers, you're going to have a challenge. But the pump and re-injection system, obviously we're not changing the chemistry and we're putting it back where we got it. So that's an easier sell, but you have to have a lot of assurances that you're not going to impact that aquifer or any of the groundwater. So there's a lot of things that you have to go through, and you have to prove that you're doing it correctly. And so there's challenges, but not challenges that can't be overcome.
Great. Well, thank you for your time, Brian. Again, great presentation. This recording will be on the IGSHPA website here in the next few days. And thanks everyone for joining us. We will see you next time. Have a great rest of the day. See ya.
Yep. Thank you.